Hello, welcome to Algebra 2 Common Core. Today in Lesson 8 we're going to work on graphs and zeros of polynomials with higher exponents than 2. So let's start first of all with third degree polynomials. Third degree polynomials are polynomials where the highest exponent is a 3. They have the name cubics. And fourth degree polynomials will be polynomials whose highest exponent is a 4, and the name of a fourth degree polynomial is a quartic, Q-U-A-R-T-I-C. So we're going to take a look at a little bit of review from what we did in the last lesson. In my first column in the table, I've got a function that's a cubic function because its highest exponent is a 3. So the first box on the top left is going to be when my coefficient, my leading coefficient, is greater than 0. So that tells me that my leading coefficient is going to be positive. Now think from the last lesson, we know what this kind of cubic function would look like because I see that I've got an odd exponent with a positive leading coefficient. So think about it for a second and remember that the graph should look something like this. Now I'm just drawing a general form, and of course the general form is that the graph starts in the lower left-hand corner and rises to the upper right-hand corner. So I'd like to introduce some notation today where we can state that. As x approaches positive infinity, so that says what's happening as my input is a number that's on the right side of my graph. Clearly I can see that the function is getting bigger and bigger, so that tells me that my outputs are also approaching infinity. So we use this arrow notation to describe what the function is approaching. Likewise, if I look on the left side of the graph, where x is approaching negative infinity, so that means that I'm going this direction with my input values, I see that my output values are going down into the negative values, and eventually they'll get very large in the negative way, so we will call that negative infinity. So the way that we read that is, as x approaches negative infinity, f of x also approaches negative infinity. Now in the second box, the one right below it, I see that now my leading coefficient a is less than 0. So that tells me that my leading coefficient is going to be negative. All that means is that the graph that I had above will be reflected over the x-axis. So if I reflect it over the x-axis, it's going to look something like this. And again, I'm just drawing a general form of a cubic whose leading coefficient is negative. It's got odd exponents as its highest exponent, so therefore I know that the tails go to opposite sides. This time when I look at the graph, as x approaches infinity, that means I'm going this way on my graph. I'm looking at the right end of the graph. The function value, or the outputs, are approaching negative infinity. So as x approaches infinity, f of x approaches negative infinity. Now look on the left side of the graph. So as x approaches negative infinity, I'm going this way on my graph, and I can see that the outputs, the function values, are getting very large, so therefore f of x is approaching positive infinity. Let's switch over to g of x, which is a quartic function because its leading exponent is a 4. So for the first part of this, my leading coefficient is going to be a positive value because a is greater than 0. For a quartic that's got an even exponent, so remember what we learned about yesterday, when I've got an even exponent and a positive leading coefficient, my graph's going to look something like this. And again, this is just a general form of it showing the end behavior. It could do a lot of different things in the middle, but I'm just looking at that end behavior. So as x is getting very large, I see that the function values are also getting large, so we are approaching positive infinity. As x is approaching negative infinity, it's going in the same direction on that left side because it's an even function, so therefore g of x is also approaching infinity. So you'll notice that for the odd exponents, my end behavior was exactly opposite. For the even exponents, my end behavior matches. Let's go to where a is less than 0, so therefore my leading coefficient is negative. When I draw a sketch of this, I see that I've got a graph that is just reflected over the x-axis. So it's going to look something like this. And again, I'm most concerned about the end behavior, or what happens on the right and left-hand side of this graph. This time, as x is approaching infinity, as x is getting really big, my graph is getting very small in the negative direction. So I'm going to say g of x is approaching negative infinity. As x is approaching negative infinity, g of x also approaches negative infinity. And again, I see that correspondence for even exponents or even functions, the ends are going to match. What tells me which way it goes is that sign of the leading coefficient. Now today we're going to practice looking at different kinds of functions and especially focus on the x-intercepts. Remember that x-intercepts have two other names. They can also be called zeros, or they can also be called roots. So when I'm asked for any of those three things, I'm really just looking for where the graph crosses the x-axis. Now today, this is going to require using your graphing calculator. So I need you to go get your graphing calculator and enter the equation for a into your calculator and make your window match the window that is on this piece of graph paper. So go from -5 to 5 on the x-axis and -20 to 20 on the y-axis. When you come back, we're going to graph this function. Welcome back. When I did this graph, I found that the first place where the graph crossed the x-axis was at -2. So -2 is one x-intercept. It also crosses at +1, so I have an x-intercept there, and again at the number 4. So this particular cubic function has 3 x-intercepts. You'll notice that the a value, the leading coefficient of x cubed, is positive. So since the a value is positive, the graph that I saw on my calculator made sense. I started in the lower left-hand corner, I went up, back down through that root, and back up through this root. Now, the very nice part about polynomial functions is that I can take that information about the roots. So let's list down the roots that we found. X is equal to -2, +1, and +4. So I can take those roots and I can actually tell what the factored form of this cubic function is by putting in the factors that would have been required to get these 3 roots. So in factored form, my equation, because I had a root of -2, I had to have a factor of x plus 2. Because I had a root of +1, the factor had to be x minus 1. And because I had a root of 4, that tells me that in factored form I also had to have an x minus 4. Now, for this particular function, we could multiply that back out again. We see that our first term is an x cubed, so it makes sense. I do get that polynomial when I remultiply this out. What I have found is that this particular function has 3 real roots. I can tell they're real because all 3 of those numbers are real numbers. For exercise B, what I'd like to do is focus on the equation. I'm actually going to change my equation. I don't like the one that I gave you in the notes. So that one's going to get crossed out, and instead I'm going to put in y is equal to x cubed plus 9x squared plus 25x plus 17. So please enter that one in your calculator. Pause the video for a couple minutes, enter it in your calculator. Please graph it, noting where the root or roots would be, and then come back and check with mine. Now when you graph this one on your graphing calculator, and again I wanted you to use that new equation that I gave you, did you see that it only had one real root? That one real root that I found was x is equal to -1. Now what that tells me is that in my equation, in the factored form, since -1 is a root, that means that x plus 1 had to be one of the factors. Now, right now, you don't know how to get this part of your answer, so I'm just telling it to you right now. But in a couple days, we're going to see how, if we know this first root, we'll be able to figure out the rest of this polynomial that I have to multiply by. And I'll also be able to take that quadratic and solve for the other roots. As it turns out, what ends up happening here is that besides the one real root, I'm also going to end up with two complex roots. So this one has one real root and two complex roots. We'll discuss the complex roots later in the unit. Please do the same thing for C. Please pause the video, do the graph, and come back when you have your graph completed. Now this graph, also a cubic function, passes through the x-axis at x equals 0 and at x equals 3. Now when I look at the factors of this polynomial, this is one that we know how to factor using our factoring techniques. So the first factor is a GCF of 2x. I took out the 2x from all three terms. When I did that, I was left with x squared minus 6x plus 9. And of course, we should recognize that as a trinomial that we do know how to factor. So that's going to be x minus 3 times x minus 3. Another way of writing that is y equals 2x times x minus 3 squared. And for our graph, it's going to be really important for us to notice that factor that's x minus 3 squared. That 2 as the exponent is telling me a number that's called the multiplicity. The multiplicity of that factor is equal to 2. What that means is that the same factor is represented twice. When that happens on my graph, when I have a factor that's a multiplicity of 2, what happens is the graph comes down to 3, but then kind of bounces off the x-axis and goes back up again. So it doesn't cross through the x-axis when the multiplicity is equal to 2. And that's going to be really important for us to notice the difference between example A and example C. What I found for this one was that the roots were x is equal to 0 and 3, and I saw that this one had 2 real roots. So from these three examples, I hope you can see that a cubic function can have 3 roots like it did in example A, or it can possibly have 2 real roots when one of them has a multiplicity of 2, or it can have 1 real root and 2 complex roots. So those are all of our possibilities for cubic functions. Back here, 3 would have been 3 real roots as well. Let's turn to the second page of your notes and look at example number 2. Now we have the cubic function y equals x cubed minus x squared minus 12x. So the first thing we're going to do is algebraically find the x-intercepts. So of course the x-intercepts are where y is equal to 0. So let's set this function x cubed minus x squared minus 12x equal to 0. Now, since I'm algebraically solving this, I'm looking for a factoring technique. So I'm going to use the GCF and take out an x, and I'll be left with x squared minus x minus 12 equals 0. That trinomial can be factored. I want to add to get -1 and multiply to get -12, so that's going to be x minus 4 times x plus 3. So when I have the cubic function in completely factored form, I can set up my t-bar and use the zero product property, and set each factor equal to 0. And from this, I see that I have 3 real roots. So on my graph, I'm going to graph these x-intercepts. So let's see here. At 0, I've got an x-intercept. At 4, I've got an x-intercept. And at -3, I've got an x-intercept. Now, this says sketch a graph of this function, so it's not necessary for us to enter it into our graphing calculator. Instead, I want to notice that the leading coefficient a is a positive value. And again, I'm always looking at the x cubed term, and I'm seeing that its coefficient is 1, which is positive. So when that's the case, I'm going to graph this by starting in the lower left-hand corner. And I'm going to go up through the first intercept, back down through the second one. And again, you'll notice that in the factors, I didn't have any that had a multiplicity of 2, so that told me that each intercept was going to be a place where my graph crossed over the x-axis. Because I had odd exponents, I see that the end behavior is different on the left than the right. On the left, it's going down. On the right, it's going up to infinity. The other thing I notice is that when I have a positive leading coefficient, I'm going to start on the bottom left and end on the top right when I've got an odd exponent. So all this information is included here, and that allows me to draw an accurate sketch of this graph. Now in example number 3, we're not as lucky. When I look at this, it turns out to be a cubic function that has 4 terms. The problem is this one is not easily factorable. In fact, I don't see any factors at all that there's no GCF, and I couldn't even do grouping or the box method to get the factors here. So when I want to know about the largest root, I'm going to go to my graphing calculator. And I'm going to enter this function in my calculator. So I'm going to put it in my calculator while you put it into your calculator. And I want you to get a picture just on your calculator of what this looks like. And then come back and take a look at the sketch that I've drawn. So I've drawn a sketch of what I saw on my graphing calculator. I noticed on the calculator that there was 1 negative root and 2 positive roots. Now because I'm looking for the largest root, I want to find the one that is furthest to the right. So that's the root that I'm looking for. So let's recall how we do that on our graphing calculator. We're going to use the calculator and use the second calculate, which is my calculate menu. In that menu, we're going to pick the option called zeros. Sorry, I started to write intersect. I don't want to intersect. I want to use the zeros option. And I want to evaluate what is that 0. So take a minute, pause the video, and come back when you calculate that 0. If you need help doing that, please come back to me in the morning and I will go over on your calculator how to do this. We've done it quite a bit throughout the year, so I hope you remember. But if you don't, please come and ask. So when I did second calculate and I chose zeros, I got as the largest one x equals 6.73 ... And you'll notice again, I only solved for this one because the largest one has to be the one that's on the right. So this question is specifically asking me between what 2 consecutive integers does that number fall? So I can clearly see on my graph that that root is going to be between the integers 6 and 7. So this question was really just testing to see if we knew how to find a 0 on our calculator and to determine which one was the larger one. So for the next example, we're going to go back to our algebraic form. So this time we've got a quartic function, so that's an x to the 4th. We want to algebraically determine the x-intercepts, and again, every time I want an x-intercept, that means that I'm going to set y equal to 0. So my equation is going to be x to the 4th minus 5x squared plus 4 equals 0. Now, this one is actually just a trinomial, but you'll notice that my first variable is an x to the fourth. So when I factor this, it's going to give me x squared times x squared, giving me an x to the fourth. Now I want to add to get negative 5 and multiply to get 4. So those two factors are going to be x squared minus 4 and x squared minus 1. I'm going to keep going with factoring because I want to see the factors in completely simplified form so that I can see how they translate over to the roots on my graph. So continuing on with my factoring, I notice that I've got the difference of two squares, so that's going to give me x plus 2 times x minus 2. And for x squared minus 1, that's going to give me x plus 1 times x minus 1. Of course, I see that I've got 4 factors. That makes sense because I've got a polynomial to the 4th degree. So setting each of these factors equal to 0 and using our zero product property, I'm getting as my roots x equals negative 2, x equals positive 2, x equals negative 1, x equals positive 1. So let's go ahead and plot those on our graph. So there's negative 2, negative 1, positive 1, and positive 2. So 4 roots where my graph is going to cross the x-axis. I again notice that my leading coefficient a is positive. So think about what that means with a quartic function. With a positive leading coefficient and an even exponent, that tells me that my graph should begin in the upper left-hand corner. It should look like a W graph. I like to think of them as letters of the alphabet. So when I graph this, it's going to look something like this. So you'll notice that this graph crosses the x-axis at all 4 of those roots. So I see that there are 4 real roots for this quartic function. I also notice that it's got a y-intercept of positive 4. That's because when I substitute 0 in for x, I'm going to get y equals 4. This graph is symmetric, but I can see that the left side and the right side happen to match up. So that's the way that quartic function would look. Let's finish off by a little bit more complicated quartic function. And what we're going to do is use our graphing calculator because this one does not look like it's going to be easy to factor like example number 4 was. So I want you this time to start with the graph, and then from the graph we're going to be able to express the equation in factored form. So do your graph first and then come back and check the video. So take a look at your graph and see if your graph matched mine. I got this quartic function, and that again looks like a W graph. The roots for this, negative 7, 0, negative 2, 0, 1, 0, and 5, 0. So I've listed down these roots, and I see that in this case I have 4 real roots. Let's finish this example off by going ahead and writing this in factored form. So I'm going to say y is equal to, because of the root negative 7, that tells me that the factor that one came from had to be x plus 7. Because of the root negative 2, the factor that one came from had to be x plus 2. Because of the root 1, the factor that one came from was x minus 1. And because of the root 5, the factor that one came from was x minus 5. So in factored form, this quartic function is x plus 7 times x plus 2 times x minus 1 times x minus 5. In today's lesson, we could see that from the graph, finding roots on the graph allowed me to find factors in my polynomial expression. And it also works vice versa. If I know the factors in my polynomial expression, that's going to indicate what the roots are going to be on my graph. Again, we are really emphasizing the end behavior of these graphs, given whether I've got an even function or an odd function, and whether the leading coefficient is positive or negative. So that table that we made on the front of your notes is a really, really important thing to know about. We'll come back and do some more with roots and polynomial equations in tomorrow's lesson. So have a great night, and we'll see you next time. Bye-bye.